So we have the host network. We have two workers. There's 11 and 12. And let's assume that they have a single interface. Let's deploy a couple of pods in the first worker and a pod in the second worker. These all have a local host and an ETH0, and that's all they have as interfaces inside the network namespace. For them to communicate with the outer node, they're going to be provisioned as a vETH pair. So inside the pod is the ETH0, the other side of the pair is the vETH, which will usually have some kind of random identifier next to it for uniqueness inside the host. So when a pod is provisioned, the IPAM module in the CNI is invoked by the kubelet to allocate the IP address to the pod, and that will be provided to the pod network namespace. So in this case, we have 10.200, 1.4, and 1.5, and you can see in my model here, it's a host local network. So 10.200.1 is going to be in the first worker. 10.200.2 is going to be the /24 available in the second worker. These are dynamically assigned. Then for communication purposes, vETHs are all joined to a bridge, usually called CNI0, which represents the standard bridge for your CNI. It doesn't have to be called CNI0. It could be called something else, but this is kind of the out-of-the-box one. And this, in turn, will drop the IP packet directly on your host network. So I have a 10.200 packet. If I'm using KubeNet, which is the batteries included network in Kubernetes, it's common to do it this way on Google, for example, Google Cloud. It just drops the 10.200 and assumes it works. It assumes that either I have layer 2 adjacency and I don't care about there being multiple subnets, or that my network itself allows multiple subnets on the same VLAN, which in the case of Google with IP aliasing I can do. And same in the case of Azure with user-defined routes. Now, on most infrastructures, especially on-premise, this is not common. So typically, you would run some kind of CNI that has encapsulation. So Flannel is a popular alternative. And in this case, I have a tunnel interface called Flannel0, and that purely just does VXLAN encapsulation, and then we'll forward it out through ETH0. And what will happen is a UDP packet will be sent with 10.030.12 as the destination, and the inner packet will have 10.200.2.6 as the inner packet destination of the frame. Flannel also will plumb the host route. So it'll ensure that there's a daemon running on each of these worker nodes, and it effectively acts as a miniature SDN controller, keeping track of which IP ranges are mapped to which worker nodes so that each node has the kind of a static route to the pod subnets that are mapped to that particular worker node, so it knows where to send the traffic. It's all just plumbed as static routes by the Flannel daemon. And etcd, Kubernetes master, is actually used as the IP address management mechanism so that I can map these nodes to these routes. So Flannel is actually talking to the kubemaster as kind of its scratch pad to keep track of the SDN controller state, to know which hosts have which subnets, and therefore the Flannel daemon can, if there's new worker nodes or new pod networks, new subnets in the pod network, it can then map those routes and then create the static routes in the actual worker node for you. If I need to get egress outside of the cluster, the typical approach with something like Flannel or with KubeNet out of the box is that there is an IP tables masquerade rule, which is also an SNAT rule. And that will ensure that the traffic from the pod is source natted out as the host network's IP, so 10.030.11. And connection tracking will be enabled so that the return flow will be mapped back to the pod appropriately. So just to summarize, you have Kubernetes master nodes, they run etcd. You have worker nodes, they may run flannelD as a daemon, which is your SDN controller for the cluster. It talks to etcd. There's actually two modes. One is goes directly to etcd as a database. The other is it uses a kind of a convenience feature Kubernetes has, where it'll manage your IPAM for you through the Kubernetes master API server without you having to talk to etcd directly, which can be a pain in the butt. So effectively, it's using the master as kind of a database to manage of which pod IP ranges are running where, and then it'll do a host local subnet map where you'll get a /24 per worker node, and that will ensure predictability of routing for pods to particular worker nodes when you're dealing with the VXLAN overlay. And therefore, it's just unicast. There is no multicast with Flannel. There is no unknown unicast. It's just unicast. There is unknown unicast. There is ARP. ARP does occur within the pod network across the Flannel overlay. That does occur, but again, that is only unicast. There is no multicast or broadcast. Okay, and I mentioned most of these, but some of the considerations for the pod network. There's IP address management, so host local subnets are allocated per worker node. There can be custom topologies if your CNI supports it. Cisco ACI, NSX, Cilium, Calico, they all support that. You have to pick your CNI plugin. Remember, CNI is host local. It runs on the worker nodes and it plumbs Linux for you, and then potentially will talk to the external SDN controller to tell it about what's there. So in the case of, for example, NSX, because it's actually burrowing a private VLAN down to the hypervisor for the tunnel endpoints, it actually doesn't do UDP from the guest. It actually burrows down into the hypervisor. It has to tell NSX about it. So it's actually calling out and doing the plumbing with Open vSwitch and doing kind of the Linux plumbing. This is all stuff we're going to explore in depth in the second session, but you have a lot of flexibility here. But usually the CNI plugin just sets up the VETH pairs, maps it to the bridge, depending on your plugin, maps it to a tunnel interface for encapsulation, and you're done. The cloud provider does cluster-wide routes and/or firewall rules in the external SDN controller. So if you're running on Azure, this is the part that does or on Google, this plumbs the route tables in your cloud. This also can potentially open up security group if you're doing services, which we'll talk about in part 2. Policy. So Kubernetes network policy is optional. A CNI does not need to provide it. However, it's almost always recommended. You almost always need something. And the most common CNI plugin that implements this is called Calico. The reason is that the most common is that it can run in a policy-only mode where it literally just does east-west distributed firewall with IP tables, and you can delegate to any other CNI under the covers. It'll just run as long as that underlying CNI will route back to the IP tables kernel subsystem, which isn't always the case. Sometimes you're trying to avoid that for performance reasons, but if you're going to use Calico, you do need to have IP tables in the flow of packets in the kernel. Ingress to the cluster is typically handled through services, which we'll get to. If your pods are externally routable, you can talk directly to a pod, but you have to find them. And if the IPs are not static, how do you find them? You might have your own way as an app owner to do that. And there are legacy software that require the ability to have predictable IPs, and they have their own service discovery mechanism. And if that's the case, then that would be a reason why you would want your paths to be routable. And then egress, if your pods are not externally routed, how is the traffic added? Is it per worker node, as I showed you in this traffic walk, or is it some other topology? E per namespace. That's the question you have to ask when you set this up. All right, questions. I think this is probably the last topic we'll cover for today.
Yes, let's handle the questions before we end. And since we're a bit over time, if anyone from the audience has to be somewhere, don't worry, everything's recorded. So it will be available on the website in a couple of days. Now let's handle the questions. Why does the host network need to be routable to the pod network?
Well, the reason is that sometimes you're hosting system software on the pods, and you don't want to get the pod on the host network. You want it to be in the pod range. And effectively, the model wants no restrictions for software on the host to be able to get to the pods. Because the way to think of it is that the host is root. The host is God. It has all the access to what's there. Once you are on the host, if you have root on the host, you have full rights to all of the pods. And that's the model, is that the host really allows the administrator to be able to troubleshoot networking, to be able to call things on the pods. It also allows you to install daemons at the system level on the host network to be able to get to it so that there's no complication in the networking model.
The next question is the pod network subnet there by default? If yes, can it be changed?
Yeah, you can change it. Normally what you would do is you can set the /16 or whatever you want to be the overall pod network for the entire cluster. And then you can also specify the subnets. If you're using host local IPAM, like I was showing you here with KubeNet or with Flannel, you can set the subnet range that you allocate on a per host basis. It's a /24 by default, but if you want it to be bigger or smaller, you're free to do that. Just bear in mind, it's not common to run more than 100 pods or so per worker node. And Kubernetes itself, I think, recommends a maximum of 250, which is one of the challenges with bare metal Kubernetes, is that you have these big beefy servers, but if you can only run 250 pods, what's the point? Not that you can't run more, it's just that the typical recommendation is that much per worker node.
And the last question, regarding the flannel. If you can go back to the slide 55, I believe. So without flannel, would the 10.0.30.12 respond to ARP from 10.202.6?
Yes. If I didn't have flannel and my underlying network was L2 adjacent or allowed multiple subnets on the same VLAN, then yes, it would just work with using standard ARP. If I'm using flannel, effectively, I would have that packet go out and it would notice in the network plumbing that it was looking for an IP that was on the host network, not on the pod network, and it would ARP for that appropriately.
Stuart, if you can go, I think 2 slides back, just before flannel. So in here, what could happen is either you could have the pod network directly connected to the physical network, in which case, obviously, the ARPs would go across the physical network. Or if you have a router in between the pod subnet and the physical network, then obviously the router would respond to the ARP request because the other node is in another pod on another host, which is another subnet.
Yep. Yeah, if you're using Calico, that's exactly how it would work. Yes. There were a few questions that we had about how is ARP handled and how do the routes get plumbed across the nodes with flannel. I'm going to actually go into greater detail in the next session with diagrams and actual MAC addresses and kind of raw ARP tables and whatnot. But let's talk about it at a high level here today, and I can also answer any questions about it. To level set, here is a simple Kubernetes 2-node cluster with 2 worker nodes. The hosts are denoted as S0 at the bottom. We have 10.0.30.11 and 10.0.30.12, the 2 worker node hosts. And then we have pods on top of it in the 10.200/16 range. Now, if you recall from last time, we discussed that IP address management, the way that you allocate subnets to individual worker nodes, is done in a kind of a block allocation type manner with flannel. So each worker node will get a /24 carved out of the broader pod network, which is a /16. And so in this case, we see here that worker node 1, which is the .11 node, that has a 10.200.1/24 range. And it's not written here, but that's effectively what to think of. And then worker node 2 here has 10.200.2/24. Those are the 2 ranges. And so the question was, okay, so say I have an application on pod 4 here, which is the 1.4 IP address. And let's say I want it to talk to 1.5. Is there ARP request and ARP reply in that scenario? And the answer is yes. So with flannel, by default, it leverages a CNI plugin. The CNI is the container networking interface that Kubernetes delegates to when it's plumbing the Linux constructs and potentially SDN controller constructs when it's setting up Kubernetes. And the bridge plugin creates bridge to either your outer network and also to potentially an encapsulation interface like Flannel 0, which will do VXLAN encapsulation. So the CNI 0 bridge is joined to all the virtual Ethernet pairs. You see VETH XYZ and VETH UVW here in the first node. Those are all effectively layer 2 adjacent for the purposes of cross-pod communication within the single node. So CNI 0 will effectively forward the ARP request from 1.4 directly to 1.5, which will reply back to 1.4. Now, do keep in mind that unknown unicast and multicast cannot be traversed over this link. Only ARP is traversed across these pods. So the way to think of it is that the CNI 0 is a bridge for cross-pod communication, but it also is a gateway. It will have the 10.200.1.1 address, and it acts as a layer 3 gateway for being able to access the service network or being able to access the host network. So this means that IP tables and whatnot can process the traffic. It will ARP out to the CNI 0 gateway and then be processed by IP tables, maybe denetted if it's sent out to outside of the overlay network to the host network. Or if it's, say we have a pod on this first worker node, it needs to talk to a pod on the second worker node, which is like, say 1.4 is talking to 2.6. In that case, the packet will be sent to the CNI0 gateway, which will then be encapsulated by Flannel 0 and sent out on the underlay network. Now, the other question folks had was, well, how is this plumbed? How normally VXLAN, there is kind of a flooding and learning approach to determining where the virtual tunnel endpoints are, the VTEPs, and having an internal table of MAC addresses and IP addresses. As I said earlier, this will be something we'll actually show in detail in the next session, but just verbally to walk you through it, there are three things. Flannel is very elegant in its most recent releases at understanding what needs to happen. Flannel is just keeping track of how many worker nodes exist. And once it sees a worker node exists, it plumbs three things in the node. It creates an IP route, which is the /24 for each worker node, is statically allocated. So think of the Flannel daemon as an SDN controller that runs on every worker node. And it's a distributed SDN controller. It's not centralized. And they're all looking at a shared database, which is the Kubernetes master, the etcd database in the Kubernetes master. And Flannel is watching that for new nodes to show up, getting a new subnet, a new /24. If those show up, it will plumb the static route. The second thing it will plumb is the ARP entry of the Flannel 0 MAC address, so that when the packets do traverse, they're pointing to the other Flannel 0 on the remote node. And the third thing it will plumb is a FDB, a bridge forwarding database entry, mapping the other way of the IP address of the other tunnel endpoints to the MAC address of the Flannel interface. This allows inbound ingress and egress for the Flannel overlay to get plumbed. And by doing this, that's all that has to happen is if a node shows up or disappears, gets a new network, that's the only control plane flutter that occurs inside these nodes. Otherwise, it's pretty static and the data plane is very stable. Even if, say, the Flannel daemon goes down, all of your routes and FDB and MAC entries are there installed permanently in the Linux kernel. And so if you wanted to upgrade or you had an outage, say, in the Flannel daemon, it wouldn't impact your data plane. Hopefully that clarifies things. It's only unicast, as I mentioned, internode and also across nodes. There is no multicast or broadcast. Okay, so that hopefully clarifies things with the packet walk.